Hello, I'm Jeff Lowe. I am a Lillian Gilreath postdoctoral fellow in the departments of chemical engineering and chemistry at Purdue University. But today I'm going to talk about my work I performed during my PhD at the University of Michigan with my advisor, Don Siegel. In this work, I used DFT calculations to probe the interface between lithium metal and its native oxide to understand how this interface may impact performance in lithium metal batteries. And thank you very much for coming to attend my presentation today. Okay, so let's get started. But before I get into the details of my presentation, I just want to mention that I'm a faculty candidate. Maybe not a complete surprise since this is a faculty candidate session. But this presentation is one of 4 presentations that I have at AICHE this year. There are 2 other presentations on the work I've been performing in my current postdoc at Purdue and a faculty candidate poster. I encourage you to check out those and to find out more about me and my research. If you would like to reach me to chat a little bit more about my research and my qualifications for a faculty opening at your institution, just send me an email. My email address is at the bottom of the slide, and it's also at the end of my presentation today. So to start my discussion today, I want to briefly go over the current state of the art in batteries, the lithium-ion battery. Now, the lithium-ion battery has taken us a long way and really revolutionized consumer electronics. However, if we want to revolutionize new industries, such as the automotive industry, we need batteries with higher energy densities. Current lithium-ion batteries use a graphite anode, so lithium ions intercalate between graphene sheets. During discharge, the lithium ions are transported to the cathode, but since the carbon in the graphite anode is not transported, in this battery it's basically dead weight, and it reduces the capacity of the battery. If instead we go to a fully metallic anode, in principle the entire anode can be transported as ions, and we can achieve significantly higher capacities. In fact, these are an order of magnitude higher in lithium metal batteries than in current state-of-the-art lithium-ion cells. Nonetheless, when we go to new battery chemistries, there are of course new sets of challenges. In lithium battery chemistries, one of the main challenges is the formation of the solid electrolyte interface, or the SEI layer, which occurs when the electrolyte decomposes upon reaction with the anode. In order to have a successful battery, the SEI should first prevent the formation of dendrites, which are these structures that form due to inhomogeneous deposition of lithium metal, and when they grow to a large enough size, they contact the cathode, they short circuit the battery, and this leads to those fires and explosions that we hear about so often in the news, and we really want to avoid. Secondly, we must allow for the transport of lithium ions. In state-of-the-art lithium-ion cells, somewhat fortuitously, electrolyte decomposition is self-limiting, so the SEI only grows to a certain size, and the lithium ions are able to be transported through its thickness. In lithium metal batteries, this isn't necessarily the case. Thus, the SEI layer is very complex, and we need to better understand the composition of this layer to successfully commercialize these next-generation battery technologies. So I thought about this challenge, and after thinking about this a little bit, I realized that any battery employing a lithium metal anode, there's one component of the SEI that won't change: lithium metal's native oxide layer. Lithium metal is extremely prone to oxidation. The black coating on this lithium foil is lithium oxide. So even in lithium metal that comes from a vendor, an oxide layer will be present. Some past studies have assessed the composition of the native oxide layer using X-ray photoelectron spectroscopy, or XPS, and have all generally agreed that there's a layer of lithium oxide, or Li2O, in direct contact with lithium metal. So in my work, I wanted to model this lithium-lithium oxide interface using DFT. To do so, I considered multiple interface models: 2 crystalline interfaces with differing terminations of the lithium oxide layer, resulting in stoichiometric and oxygen-rich compositions, and an amorphous interface which was grown through the stepwise addition of oxygen molecules to a lithium surface. Well, the crystalline interface is what's typically created to study these types of systems with DFT, but I felt it was important to also create an amorphous interface that more closely mimics the process by which the native oxide layer forms in nature. And in my knowledge, this is one of the first detailed analyses of the native oxide layer. The work I'm discussing today was recently published in ACS Applied Materials and Interfaces. I won't be able to go into all the details in the paper in today's presentation, so I encourage you to look at the paper if you want more specific details. So let's start with the crystalline interfaces. To create the stoichiometric system, I started with the lowest energy Li2O surface, the 111 termination. Then I selected the lithium metal surface among the 3 low index surfaces with the lowest strain with the Li2O 111 surface. This happened to be the 111 termination, and it gave a very low strain of only 1%. I then optimized the structure with DFT to achieve the final structure shown at the right. For the oxygen-rich interface, I performed an analogous procedure. So now that we have the crystalline interfaces, we can talk about the first SEI requirement that I mentioned earlier. We need to prevent dendrite formation. It has been suggested in the literature that if lithium is able to strongly wet a surface, there will be a decreased propensity for dendrite formation. So what I mean by this is that when the battery is being charged and discharged, lithium is plated and stripped at the anode. So when lithium is plated, we can assess wetting by looking at the contact angle lithium makes with the surface. And rather intuitively, if lithium has a smaller contact angle, it more strongly wets the surface. And then it will spread out across the surface, giving a more even deposition, and thus a decreased propensity to form dendrites. The parameter that we use to assess wetting is the work of adhesion, which determines how much energy it requires to separate interface. Looking at the work of adhesion for the stoichiometric and oxygen-rich interfaces, we see that the work of adhesion in the oxygen-rich system is more than 30 times larger. Thus, lithium should strongly wet a surface with exposed oxygen atoms, and a surface with exposed oxygen atoms should show a decreased propensity for dendrite formation. Now let's take a look at the amorphous interface. I'm going to play a video showing the dynamic evolution of the interface while I describe how I created the interface. I initially started with the same lithium surface as in the crystalline systems. Then I added an oxygen molecule above the surface, allowed it to dynamically evolve forward in time following Newtonian mechanics using 4 picoseconds of ab initio molecular dynamics at room temperature, and repeated this procedure for 10 more oxygen molecules for a total of 11 oxygen molecules. I've colored the most recently incorporated oxygen molecules yellow to distinguish from those that are already in the interface. And as you can see, the most recently incorporated oxygen molecules drive oxygen diffusion in the system by pushing the other oxygen atoms deeper into the slab. Notice that I increased the size of the lithium unit cell about right here by adding bulk lithium atoms to the bottom of the system so that I can create a thicker interface. In the end, the lithium oxide layer achieves a thickness that is roughly equivalent to about 2 monolayers of crystalline Li2O. So now let's look at the crystalline and the amorphous models. The way I've done this is to assess the interfacial energies of each of the systems. The interfacial energy is the energy of the interface relative to bulk lithium metal and lithium oxide. Here I'm showing the interfacial energy as a function of relative oxygen chemical potential, which gives the chemical potential of oxygen in Li2O relative to the chemical potential of oxygen in oxygen gas. That's because we don't know the chemical potential of oxygen in Li2O or of lithium in Li2O. We can define the full range of possible chemical potentials by considering 2 limiting cases. We can have an equilibrium between the chemical potential of oxygen in Li2O and the chemical potential of oxygen in oxygen gas, which is equivalent to a relative chemical potential of 0. Or we can equate the chemical potential of lithium in Li2O to that of lithium in bulk lithium metal, which gives a relative chemical potential of -6 based on the DFT computed formation energy of bulk Li2O. So now if we look at the values, we see that the oxygen-rich interface is always negative, whereas the stoichiometric interface is always positive. So the oxygen-rich interface is energetically preferred, and it's also more favorable than separating the interface into bulk lithium metal and lithium oxide. If we include the amorphous interface, it's lower in energy than both crystalline interfaces and is thus the most probable model under equilibrium conditions. Now let's assess the electronic structure of the Li2O interface. One way to assess the electronic structure is to look at the core level electron binding energies for lithium 1s electrons in different binding environments, which for our purposes is lithium metal and Li2O. This is equivalent to determining energies from XPS. This technique is not very common in the computational literature, so I wanted to benchmark the core level shifts, which are relative electron binding energies. Here I computed the binding energies relative to lithium carbonate, since lithium carbonate has the least amount of variation in the data set of experimental core level shifts from the XPS that I used. In the plot to the right, I'm showing the computed core level shift on the y-axis and the experimental core level shift on the x-axis. The dashed line is the line of agreement between the two. For the experimental data, I'm using a dataset compiled by Kevin Wood at UCSD. I believe that the way he thinks about XPS data is really the best way to analyze it, since each study reports a different core level shift for different phases. So we really need to think about the deviation in these values. In this plot, I show the standard deviation in the experimental data set by error bars. And as you can see, with the exception of lithium hydroxide, the computed data is well within the experimental standard deviation of each phase. And in particular, there's very good agreement for lithium metal and lithium oxide, which is really what matters for the current study. Now we can compare the core level shifts between the stoichiometric crystalline interface on the left and the amorphous interface on the right. I'm showing the stoichiometric crystalline interface, but the oxygen-rich interface has the same trends. The core level shift values are referenced to bulk lithium metal, as you can see here. And starting with the crystalline system, we see that the core level shifts in the bulk portion of the slab roughly match the values in bulk lithium metal, and the shifts in the oxide portion are higher in energy. That's because the binding energy, which is a difference between the energy of the excited state, where a core electron has been excited to the valence band, and the ground state, is lower in lithium metal than in lithium oxide due to screening of the 2s electrons, or by the 2s electrons. In between the oxide and metallic regions, there's a broad transition region, roughly 6 to 9 angstroms wide. This region is significantly larger than the width of the interface, as determined in deviations in the atomic structure, just by looking at the structure of the interface. Now, in the amorphous system, the oxide and metallic regions are not as well defined. There's a transitional region, and it's even wider than in the crystalline system, but it's complicated by the vacuum portion on either side of the slab, which has the effect of increasing the electron binding energies relative to the bulk. Well, the takeaway messages for the electronic structure are twofold. The width of the Li2O interface is 1, wider than what's determined by the atomic structure, and 2, underpredicted by the crystalline models. Keep in mind that the amorphous interface is the lowest in energy and more likely to be present in nature. So, studies that only assess crystalline interfaces, which as I mentioned earlier in the talk, are the most common in the literature, will underpredict the size of this interface based on the electronic structure. Now let's discuss the second SEI requirement that I mentioned at the beginning of the talk. The SEI must allow for the transport of lithium ions. So the question is, how well are lithium ions transported in this amorphous interface? To assess this, I computed the self-diffusivities of lithium ions at 4 different temperatures and plotted the results in an Arrhenius plot. Each point is an average of 3 separate ab initio molecular dynamics trajectories run for 40 picoseconds, which is a non-trivial simulation time for ab initio MD. From the Arrhenius plot, we can compute an activation energy for diffusion of 0.41 EVs. To put this in context, we can compare this value to fast lithium-ion conductors in the literature, and we see that 0.41 is at the upper end of the regime. So this interface is a good lithium-ion conductor. The final question is, how does this compare with experiment or other values in the literature? Well, the computed lithium-ion diffusivities are roughly 3 orders of magnitude larger than in bulk lithium Li2O from past experiments. Taking this a step further, there was an excellent experimental analysis from the Gallant group at MIT that came out earlier this year where they very carefully deposited a layer of Li2O and only Li2O on a lithium metal slab. And as I mentioned earlier, this is pretty hard to do. Much like us, they were interested in separating the effects of lithium oxide with other components that are likely present in the SEI and lithium metal batteries, since the SEI is so complex. They performed electrochemical impedance spectroscopy on this Li2O system, and what they found was that their experimentally measured lithium-ion diffusivities were 3 orders of magnitude larger than those in bulk Li2O in past studies, much like what we found. Further, if I extrapolate my computed lithium-ion diffusivities down to the temperature at which they measured theirs, I get a value on the order of 10 to the negative 9th centimeters squared per second, which agrees very well with the values they measured. An order of magnitude agreement is about as good as you can get with diffusivities. Also, don't pay too much attention to the x-axis here. It's not the temperature the diffusivities were measured at, but the temperature at which the Li2O surface was annealed at. These measurements were all around room temperature. So we have very good agreement between theory and experiment, or computation and experiment. But what does this all mean? Well, this suggests that we can likely improve the transport of lithium ions by increasing the percentage of amorphous Li2O in the SEI. So to conclude, metallic lithium is a promising anode material due to its high specific capacity. And in this work, I showed one of the first detailed analyses of the interface between lithium metal and its native oxide. I explained that there are 2 key properties of the SEI governing the performance of lithium metal batteries. One, we need to prevent dendrite formation, and one of the ways we may be able to do this is by creating an interface with exposed oxygen atoms. And 2, increasing the percentage of amorphous Li2O in the SEI may improve the transport of lithium ions through the interface. I'd like to thank my advisor, my PhD advisor, Don Siegel, for his guidance during this work, to members of my group, and to Neil Dasgupta and his PhD student Eric Kaziak for helpful discussions on the experimental side. I would also like to thank Jay Caesar for funding this work, the Davidson School of Chemical Engineering at Purdue for conference support, and the College of Engineering at Purdue for supporting my current fellowship. I look forward to any questions you may have during the scheduled Q&A for this presentation. If you aren't able to attend, just send me an email. And thank you very much for viewing my presentation today.